two projects. In this video, we are going to explain about the project title Face and Audio Live Detection. Introduction. In an increasingly digital world where interactions are becoming more virtual and remote, the ability to understand human emotions in real time has become a crucial aspect of various applications and technologies. The project Face and Audio Live Detection aims to address this need by developing a sophisticated system capable of detecting and analyzing facial expressions and audio sentiments in live video streams. Understanding human emotions is fundamental in numerous fields, including but not limited to human computer interaction, mental health assessment, and customer service. Traditional methods of gauging emotions often rely on subjective interpretations or manual assessments, which can be unreliable and time consuming. By leveraging advancements in computer vision and machine learning, this project seeks to create an automated system that can accurately detect and interpret emotions from both facial expressions and audio cues in real time. The scope of the project encompasses the development of algorithms and models for real time facial expression recognition and audio sentiment analysis. Specifically, the system will be designed to identify a range of emotions, including happiness, sadness, neutrality, and disgust, from both visual and auditory inputs. Furthermore, the project aims to integrate these capabilities into a unified platform capable of processing live video and audio streams. The project utilizes state of the art techniques in deep learning and pattern recognition to train models for facial expression recognition and audio sentiment analysis. Large data sets containing labeled examples of facial expressions and audio recordings will be used to train and fine tune these models. Additionally, the system will employ real time processing algorithms to ensure efficient and timely analysis of incoming video and audio streams. Objective. The overarching goal of the project is to develop sophisticated algorithms and models capable of analyzing live video streams and audio inputs in real time. This capability will empower the system to detect and interpret emotions as they manifest, whether through facial expressions in the visual domain or through tone, pitch, and speech patterns in the auditory domain. To achieve the detection and classification of facial expressions, the project leverages computer vision techniques, notably convolutional neural networks CNN and residual networks ResNet. These deep learning architectures are particularly adept at processing visual data, enabling accurate recognition and classification of facial expressions. By training these networks on labeled datasets containing examples of various facial expressions, such as happiness, sadness, neutrality, and disgust, the system learns to distinguish between different emotional states based on facial cues. In addition to visual cues, the project implements methods for analyzing audio inputs to extract emotional cues. This involves examining characteristics such as tone, pitch, and speech patterns. By discerning subtle variations in these audio features, the system can infer the emotional states conveyed through speech. For instance, it can identify cues associated with happiness, sadness, or disgust in spoken language. One of the key aims of the project is to enhance user experiences by providing real time feedback based on the detected emotions. By integrating the emotion detection capabilities into interactive systems, the project enables personalized interactions and adaptive interfaces. For example, if the system detects that a user is expressing happiness, it adjusts its response or recommendations accordingly to align with the user's emotional state. This could involve suggesting content that matches their mood or tailoring the interface to provide a more engaging experience. Software and hardware requirements. Software requirements of the project are: application is Anaconda, primary language is Python, front end framework is Flask, back end framework is Jupyter Notebook, database is SQLite 3, Front-end technologies used in the project are HTML, CSS, JavaScript, and Bootstrap 4. Hardware requirements of the project are operating system of Windows, processor of Wi-Fi and above, RAM of 8 GB and above, hard disk of 25 GB and above. Working modules or flow of work. To implement this project, we have designed the following modules. The first module is importing libraries. This module involves importing necessary libraries and packages required for various tasks in the project. Commonly used libraries include TensorFlow or PyTorch for machine learning, NumPy for numerical operations, Matplotlib or Seaborn for data visualization, and Flask for web development. Importing dataset. In this module, the dataset containing facial and audio data is imported into the project environment. The dataset includes images for facial recognition and audio files for audio signal processing. These datasets serve as the basis for training and testing the machine learning models. Data visualization. Data visualization is crucial for understanding the characteristics and distributions of the dataset. This module involves creating visualizations such as histograms, scatter plots, and heat maps to explore relationships between features, identify patterns, and detect anomalies in the data. Data augmentation. Data augmentation techniques are applied to increase the diversity and size of the dataset, which helps improve the generalization and robustness of the machine learning model. Common augmentation techniques for images include rotation, flipping, scaling, and adding noise. While for audio data, techniques like time stretching, pitch shifting, and noise injection are used. Feature extraction. Feature extraction involves transforming raw data into a more meaningful representation that can be used by machine learning algorithms. For facial data, features such as facial landmarks, textures, and colors may be extracted, while for audio data, features like MFCCS, MEL frequency cepstral coefficients, spectrograms, and pitch are extracted. Data preparation. In this module, the dataset is pre-processed and prepared for training the machine learning model. Pre-processing steps include normalization, scaling, encoding categorical variables, and handling missing values to ensure the data is in a suitable format for training. Splitting data. The dataset is split into training, validation, and testing sets to evaluate the performance of the machine learning model. The majority of the data is used for training, while smaller portions are reserved for validation to tune hyperparameters and testing to assess the model's generalization ability. Building the model. This module involves designing and implementing the architecture of the machine learning model. For facial and audio detection tasks, convolutional neural network CNNs and recurrent neural network RNN are utilized, along with architectures like ResNet for improved performance. Training the model. The model is trained using the training data where the parameters of the model are adjusted to minimize the loss function. During training, the model learns to make predictions based on the input data and the corresponding labels. Flask framework with SQLite for sign up and sign in. Flask, a Python web framework, is used to develop a web application that allows users to sign up and sign in to the system. SQLite is employed as a database to store user credentials securely. User gives input. Users input their data, which is then pre-processed to ensure it is in a suitable format for prediction by the trained model. Pre-processing involves resizing images, converting audio files to spectrograms, or applying other transformations. The given input is translated and pre-processed for prediction. Trained model is used for prediction. The pre-processed input data is fed into the trained machine learning model for prediction. The model outputs predictions based on the learned patterns and features from the training data. Final outcome is displayed through front end. The final outcome, which includes detected faces, recognized individuals, or classified audio events, is displayed to the user through the front end of the web application. This provides users with actionable insights and feedback based on the input data. Algorithms used. To implement this project, we have designed the following algorithms. The first algorithm is CNN, Convolutional Neural Network. CNNs are deep neural networks specifically designed for processing structured grid-like data such as images. They consist of convolutional layers, pooling layers, and fully connected layers. Convolutional layers apply learnable filters to capture local patterns and features within the input data. Pooling layers downsample feature maps to reduce computational complexity and overfitting. Fully connected layers connect every neuron in one layer to every neuron in the next, enabling the network to learn high level representations. CNNs automatically learn hierarchical features from images during training, making them effective for tasks like image classification, object detection, and segmentation. Coming to the next algorithm, which is ResNet, Residual Neural Network. Residual neural networks are a type of deep neural network architecture that introduced residual learning to address the vanishing gradient problem in very deep networks. ResNets utilize residual blocks containing skip connections that bypass one or more layers. These skip connections facilitate gradient flow, mitigating the vanishing gradient problem and enabling training of deep networks with hundreds of layers. By stacking multiple residual blocks, ResNet architecture achieve increased depth while maintaining or improving performance. Deeper networks capture more complex features and achieve higher accuracy on tasks like image classification and object detection. ResNets such as ResNet 50 and ResNet 101 are widely adopted in computer vision due to their effectiveness in learning hierarchical representations. Performance comparison graphs. Models are compared with the evaluation metrics accuracy, precision, recall, and FN score. This is the accuracy comparison graph. Here on the x-axis, we have the algorithm name, and on the y-axis, we have the accuracy score. Accuracy is a measure of the overall correctness of a classification model. It calculates the ratio of correctly predicted instances, both true positive and true negative, to the total number of instances. This is the precision comparison graph. On the x-axis, we have the algorithm name, and on the y-axis, we have the precision score. Precision is a metric that assesses the accuracy of positive predictions made by the model. It calculates the ratio of true positives, correctly predicted positive instances, to the total number of positive predictions. True positives plus false positives. This is recall comparison graph. On the x-axis, we have algorithm name, and on the y-axis, we have recall score. Recall, also known as sensitivity or true positive rate, measures the model's ability to correctly identify all relevant instances in the dataset. It calculates the ratio of true positives to the total number of actual positive instances, true positives plus false negatives. This is the FN comparison graph. On the x-axis, we have the algorithm name, and on the y-axis, we have the FN score. FN score is the harmonic mean of precision and recall. It is a balanced measure that considers both false positives and false negatives. It is calculated as 2 times the product of precision and recall divided by the sum of precision and recall. It provides a single metric that balances precision and recall, making it useful when we want to consider both false positives and false negatives in the evaluation. Execution. To execute this project, first we need to open the code folder which contains the project source code files. This is the code folder. This is the static folder. This folder consists of files related to CSS, JavaScript, and Bootstrap. This is the templates folder. This folder contains all the HTML pages used in the project. It typically includes files like index.html, about.html, and more, which represent different pages of the website. This is app.py file. This .py file contains the information related to front-end logic. It includes code written in Python that handles server-side operations such as processing user requests, interacting with the database, and generating dynamic content to be rendered in the HTML templates. This is model folder, which contains algorithm information which will be loaded into the project code during runtime. This is notebook.ipynb file. This is a Jupyter notebook file which contains a combination of code, graphs, and outputs all in one place. It allows users to write and execute code in individual cells, making it a popular choice for data science. This is signup.db file. This file is the database file used to store user information. First, we need to copy the path of the code folder from the address bar of the file explorer. Here, I'm copying the path. Now open the Anaconda prompt. Use the cd command followed by a space and paste the copied path and hit enter. This command will execute the Python script and perform a runtime check for any syntax errors or logical issues. Now type python space app.py and hit enter. After running the app.py file, the Flask framework will host the application locally at the default address localhost, which is this, and port, which is this. Now copy this local link provided by the Flask framework. I'm copying the link and paste this copied link into any web browser. I usually prefer Google Chrome and hit enter. The homepage of the project is displayed in the browser. This is the front end built using Flask framework. Click on login link. Here we need to enter the username and the password which we have registered, and then click on login button. We have logged in successfully. First, we will initiate live audio detection. So for that, we need to upload the audio file, and after uploading the audio file, we will predict the emotion type of the audio. Click on choose file to select the audio file. So here we have the audio files which we have recorded. So I'm selecting the first audio and then click on open and then click on upload button. So here we can see the result for the given input audio. The emotion type is surprise. Let us upload some more audio files and check the emotion type. Click on try again. Click on upload button. So here we can see the result for the given input audio. The emotion type is angry. Let us upload some more audio files. So here we can see the result for the given input audio. The emotion type is sad. Let us upload one more audio file. So here we can see the result for the given input audio. The emotion type is happy. In this way, just by uploading the audio files, we can predict the emotion type of the audio, whether it is happy, sad, fear, or calm. Now we will initiate live video detection of facial expressions. For that, click on face expressions link. Once clicked, the camera will activate, enabling real-time detection. We will notice the camera is now on. So here we need to give some facial expressions, and after giving the facial expressions, we can see a bounding box, and on top of the bounding box, we can see the facial expression as neutral, happy, or sad. So here I'm giving some of the expressions, and we can see on top the name of the expression as happy, sad, or neutral. Now close the camera. In this way, the system will provide the corresponding expression analysis in real time. Now click on sign out link. Conclusion of the project. The project has achieved the successful development of a real-time surveillance system capable of detecting both facial and audio signals. This system operates in real time, enabling prompt responses to security threats and incidents. By combining facial and audio signal detection, the system enhances overall security measures and situational awareness. The project has implemented machine learning algorithms such as convolutional neural networks, CNNs, and ResNet, which have demonstrated effectiveness in accurately detecting and recognizing facial and audio signals. CNNs excel in learning hierarchical features from visual data, while ResNet addresses challenges associated with training deep neural networks, ensuring robust performance in detection tasks. The capabilities of the developed surveillance system contribute to enhancing security measures and providing valuable insights for various sectors, including law enforcement, public safety, and entertainment. By detecting and analyzing facial and audio signals in real time, the system assists in identifying potential security threats, managing crowd behavior, and ensuring the safety of individuals in diverse environments. Future research could focus on exploring additional features and refining model architectures to further improve the accuracy and efficiency of the surveillance system. Optimization efforts could target scalability and efficiency enhancements to accommodate larger data sets and real world deployment scenarios. Additionally, incorporating advanced anomaly detection techniques and exploring multimodal data fusion approaches could enhance the system's capabilities for detecting and mitigating security risk effectively. These recommendations aim to advance the field of surveillance and security, addressing evolving challenges and requirements.
Thank you for watching video. For more projects please visit our website www.trueprojects.in. For updates on latest project videos, please visit True Projects YouTube channel and subscribe.